Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Today we're in part 3 of the 3-part series on constructing binary trees from various traversals. In the first 2 videos we covered the pre-order in-order combination, then the post-order in-order combination, and today we're doing away with the in-order altogether and doing just the pre-order and post-order. I'd argue that this one is significantly more difficult than the other two. Maybe that's just my opinion, but I struggled the most with this one, definitely to wrap my head around it. And I think I finally got a concise, succinct explanation on how to do it. I think it's a great question. It doesn't seem to be asked too much. Bloomberg and Amazon have asked it a bit, but nonetheless, like I said, I think it's a really good one. As the nature of the problem suggests, we need to return any binary tree that matches the given pre-order and post-order traversals. The values in pre and post are distinct positive integers. All right, so no one's trying to trick us here. What I've done with the input, I've taken the pre and the post order traversals and I've copied them over here. And just for the record, the tree that this will make will be just kind of a super vanilla 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7. All right, so I'm probably gonna get rid of this just so it doesn't take up space, but that's what we need this one in particular to look like at the end of the day. So kind of, I'm gonna try to keep this video as consistent with the other two in terms of how we're logically approaching it. And in the previous 2 videos, what we acknowledged, or one of the many things we acknowledged, was that what the order was of these traversals. So we said that in a pre-order, we always start with the root. We then check all of the left subtrees, and then we check all of the right subtrees. All right, right. Post order now is the exact opposite. So for post order, we actually start with the not the exact opposite. Sorry, we start with the left. We then go to the right, and then after those, we finally hit the root of the tree, or self, if you will, depending on how you look at it. What that tells us is this, is relatively speaking, our root's going to sit right here for pre, then we're going to have some length of a left subtree, and we're going to have some length of a right subtree. At present, I don't know what those lengths are, so I've kind of arbitrarily drawn a few lines here, right? And here we'd have left, we'd have right, and then we'd have root. All right, so we'd have left, left, that was brutal. There we go. Left, right, and root. All right. So what makes this problem a bit more difficult than when we had an in order here? Well, we were kind of spoiled with the last, and maybe I'll use the pre-order in-order combination as a reference. If you haven't seen those videos, I'd suggest you go check them out. And then you'll see how the logic kind of builds onto itself. But we had the luxury when we had, again, let's say with the pre-order in-order traversal, to say something as follows, and we would just say, I'm just going to keep one index pointing at the first root, and I'm going to jump into recursive call, and I'm going to say, well, let's create a root with this value here. And then what we'll do is we'll find that value in the in-order traversal, and maybe we had something like, let's pretend this value was 6 instead of 1. I would locate that value in the in order. Again, this isn't post. Just for the moment, let's play imaginary and then say this is in order. And I'd kind of say, well, I can acknowledge that this is my left subtree, this is my right subtree, and I had 2 indices. I had in start and in end, and I would pass those in recursively to denote either this subtree or that subtree. And that was pretty straightforward. So I'm going to do on all these. Sorry, I'm going to undo all these. And get back to reality, but that was just a refresher of kind of what we did and why we made this recursive call. And again, we only had 2 indices. I could kind of start one at start and end, which would have been this index -1, and then our new start here would have been, this index +1, all the way to whatever was at the end here, and that's how we made our calls. We can't quite do that in its exact same form here. The reason is the following. I can't really just walk along one item at a time here, because let's say that we had, if this was our left subtree here, and this represented the left subtree from the root of 1. So we kind of know for free that we do have this root of 1. And I'll pretend that this is my left subtree for a second in the pre-order, and this is my left subtree. It represents the same part of the tree, it's just in the post order. If I switch these two numbers around, the 5 and the 4, this is now a different tree. If I switch this 5 and the 4, it is also a different tree. And so the order with which these nodes fall with respect to one another within that subtree and the two different traversals matters. They both need to be taken into account simultaneously. And so when I think about making these recursive calls, I need to think about where, where along my traversal is my left subtree, where along my preorder traversal is my right subtree. And I also have to keep that into account for my post order. I go, where does my post order, where does my left subtree start and end in the post order? Where does it start and end in the right post order? So that's one thing that we need to figure. In fact, that'll be the main thing. So given that that's the case, if I can identify where these are, I'm now going to need double the parameters that I had before. I used to have 2. We used to have in start and in end. Now we're going to need to keep track of this movement for both the pre and the post order traversals, meaning that we're going to need some sort of value called pre-start and pre-end, and we're going to need post-start and post-end. And what I'm going to do here is I'm going to undo some of this. So I think this stuff is relatively clear at this point. And the reason I want to undo it is to give me a bit of space here in recognizing the following. All right. This is my root here. I'm going to start by looking at, this is kind of my, and I'm almost going to use the preorder traversal as an anchor for walking through, even though we're not going to walk through it quite as linearly as before. The reason I'm doing this is because I think it's just a bit more intuitive. At least maybe this is just like an English language thing where we write from left to right, and so it's easier for us to read that way as well. You could kind of reverse the process in the way I'm going to explain this video, with almost having your post as your anchor and going this way. I'm only choosing to do it this method because I think it's a bit more intuitive for explanation for most people. And so I can I can begin by passing in some parameters for pre-start and pre-end, and I'll call them the beginning and the end, and same thing for these two. So we'll have some arbitrary kind of beginning that's just going to span the whole array because we don't know what we're jumping into yet. We don't know how we're going to break up our subtrees. As soon as I jump in though, I do understand that my beginning, my pre-start index right here, will be the root of the tree. Okay, it will definitely be the root of the tree. So what we can begin to do is we're going to say, let me just take this root and create it. I'm going to create this root. I'm now going to have to do some other work here in determining how I'm going to make my left subtree and my right subtree. But we do know, so I'm going to move this over a bit so I have more space to write. We do know that this will be my root of the tree. Fine. Again, we could do this from the other way around, but I think this way is more intuitive. This is going to be the root of the tree. Now, if this is the root of the tree, let's remember we had this whole root, left, right business, okay? So if this is the root of my tree here, my left subtree is going to start one value over. Okay, my left subtree is going to start one value over. So at this 2, my left subtree is going to start here. 2 is going to be the beginning of my left subtree. Now, where does this actually end? Does it end here? Does it end here? Does it end here? Does it end here? Well, we don't know just yet. Sorry, I'm going to undo this, make it a bit more clean. So we were looking here, and now we said, okay, 2 is going to be the beginning of our left subtree. The quantum leap in imagination or in understanding maybe of these traversals now that we're going to need to get is the following. Pre-order goes one way, post-order goes the other way. If 2 is the beginning of my left subtree in the pre-order, then it would represent the end of the left subtree in the post-order, okay? The beginning of the left subtree in the pre-order is going to equal the end of the left subtree in the post-order. And what I mean by the end, if you will, is this. If I can identify this 2 in the post-order traversal right here, they represent the same node, that will be the end of my left subtree. The beginning will be, well, all the way here. This is going to represent my left subtree for that reason. And I'm kind of, we can think through this as we're making a recursive call on our initial call with these traversals and not necessarily as we're taking further steps down. If we can understand how to set up the first recursive call we're going to make, the rest of them we're gonna get for free. We're going to get for free, all right? If this is where I'm gonna start my left subtree, and when I say start, I mean in terms of like figuring out what part of this array it spans, that span is going to have to end at that spot in the post-order traversal, so right here. So this is my step one. I almost acknowledge step one. Step two is to find where it is here. Step three is to say this is where my left subtree would end. And notice that it is 3 units long. Okay, we've got 4, 5, and 2. It's 3 units long. That means that in the pre-order, it must also be 3 units long. So it must go out to here. And this is kind of my fourth step. This is going to be my left subtree for for this entire tree. So what does this tell us? If we had, so I'll redraw these dots. So again, I started here, I found it in here, and to kind of find this value in the post order traversal, we're going to set up a really quick hash table with the values and the indices, just so we know where to point to in constant time. So I acknowledge this is my end. I'm going to go all the way to the start for my beginning, and then all the way from my start, or sorry, this length. So we can find this length. This length is 3, and then we're going to acknowledge that length right over here. The way we're going to do that and how we're going to set up our variables is as follows. This is going to be my let me do it this way. I have some notes here on, I kind of wanted to make this really as understandable as possible. I'm going to get rid of this one for now because I really want to make these notes super clear for you guys on how we're actually going to make a recursive call on our left subtree and how we're going to make a recursive call on our right subtree. So we can acknowledge that we've made this root, and I'm pointing at this item, and that root will maybe it'll look something like this. For the root, I'll just say it's going to equal some tree node, or I'll call it node, and that node was going to have a value of I'll call this for our pre-order, and we're going to have some sort of pre-start. Like I said, I'm going to call it pre-start is going to be the variable. That's going to be the pointer, and it'll initially start by pointing at the beginning of the array. And maybe I'll kind of separate this theory out up top from the logic on how we're going to make these recursive calls. Now, to make sure that this is like extra clear, I'm actually going to go ahead and use the text tool because I don't trust myself to write very cleanly here. Let me see if I selected it. Oh, that is a wicked font. Chewy, that's not good. Can we do like Arial? Okay, I don't want to spend time changing the font, so we'll do it this way. We'll do the following. So for the left subtree, we're going to have to do a couple of things here. I'm going to say that the left subtree, oops, maybe you know what? There we go. All right, so left subtree starts at, and so I'm going to do this for pre and for post. All right, so we're going to say that the left subtree call starts at pre-start. So this was I'll kind of have like a pre-start variable at the start here at pre-start plus 1. So this is going to be our root variable, this one right here. The beginning then of our left subtree is going to be this 2 right over here. All right, we found that. So I think we kind of logically acknowledge that that's the case. And what I'm struggling to do here, guys, I don't even know how to move this text now. So maybe I got to just click off and oops, nope, that's no good. All right, you know what? We're sticking to it the old school way. I'm sorry about this. We're gonna write. What I kind of wanted to do is the following. If we had for pre and for post. So for pre, I'm gonna say the following. Our left subtree starts at pre-start. So that was originally the starting index of that node. Pre-start plus 1 unit over. So meaning not this one, but this here is going to be the beginning. All right. The left subtree ends at, so originally we had this pre-start over here, and we're going to want to end it at some, let me see here, pre-start plus the length of however long we had. So if this, imagine this was 3 units long, okay? So we had our left subtree we acknowledged was 3 units long, and we're going to calculate, we'll call that length. If I'm at index 0, I want to end it right here at index 3. So I'm just going to say pre-start plus length. What I'm going to do is I'm going to move my face up here. So this is how I'm going to be determining what my parameters are for my call. I'm going to be saying that this is my start and this is my end for the left subtree when I make my recursive call. Now, I'm going to have to acknowledge what my left subtree is with respect to my post order call as well. And for that one, we're going to say that LST, so it's going to start at, this original variable, so this post start that we had. There's nothing fancy there. Post start. And then we're going to say that the left subtree ends at, well, where's it going to end? It's going to end at this variable right here, so this 2, and we're going to find some index for this value. So for now, I'm going to call that post index for lack of a better word. But what that's going to refer to is the actual index that represents the beginning of the left subtree in the pre-order and the end of it in the right subtree. Okay, so index, and maybe I'll give myself a bit more space here. So I'll remove these and I'll redraw them a bit lower. And the reason I'm really writing these out step by step is because I think otherwise the recursive calls will get slightly confusing. And so that's why I really wanted to beat this home really clear on how it is that we're defining what our boundaries are going to be when we're making the recursive calls. This is going to be how we're going to make the calls for the left subtree. Now we're going to have to do the same thing for the right subtree and determine where those indices are going to be. So our right subtree, we said it's going to start at, well, if this one ended at pre-start plus length, so our left subtree, we know ended right here, goes here. So if this was the end of it, then we know our right subtree must start right afterwards by 1 unit. So it's going to start at pre-start, like we had up here, plus length, plus 1. So it's literally this value plus 1. We're starting 1 more unit over from the end of our left subtree. Now, our right subtree is going to end at, it's just going to end at pre-end. And I think the easiest way to think about this again and why this is the case is imagine we're doing our first recursive call here. Our original pre-start is right here. Pre-start. And this is our original pre-end. And those are our boundaries, if you will, for where we can possibly make our calls. So if I leave that one as it is, that's going to kind of take care of the entire array. Now, one more time, we're going to have to define the same recursive logic for the post order calls. Okay? For the post order calls, our right subtree is going to start at, well, remember how we found this index over here? And we said that was the end of our left subtree. Well, the beginning of our right subtree then is going to be 1 unit over because again we have this left, right, root pattern because it's a post order traversal. So we're going to take this value here, this post index, and we're going to make the call at post index plus 1 to be the beginning of our right subtree in the post order traversal. And finally, the right subtree is going to end at, well, let's think about it. We had, this was originally our, and same kind of logic here. Imagine we had a post start right here at the beginning, and this was our post end. Okay. Now you may be tempted to just say it's going to end at post end, kind of like pre-ended. But notice that post end is actually the root itself of the value of the root node we're creating. So we need to go to post end minus 1, and we're going to end it off right here. So it's going to start at the 6th and end 1 before the post end, or where the root is. So that's why it's going to end at post end minus 1. And this right over here, I know this is a lot of writing, and I don't usually like to make my videos like this with a lot of text, but I couldn't really come up with a better way to kind of describe and really drill down systematically how it is that we understand where this binary tree is split within the traversal itself. And again, the way we did that was by acknowledging here, I'm going to play around with my camera some more, was by noticing that we have the root left right pattern for the pre-order, and it's the opposite for the post. We have left right root. When we start the left subtree here in pre, we can find the end of the same left subtree in the post order. Systematically go to the beginning to find the length of it, and then kind of find that very same length or the end then of the left subtree in the pre-order using that length that we found. Right? That's how we made all of these calls. To then make the right subtree calls, we kind of do a really similar logic, except we do it on the other half of the array that we were doing. So if you still find this a bit confusing, I would urge you to pause the video and rewatch this section where we're walking through the logic. The code is going to be pretty much a replica of this, and I don't know, like I said, I didn't find this solution all too intuitive, or even I didn't find the question all too intuitive in terms of how to solve it. This is the best way that I could kind of come up with to understand, again, how to break it down systematically. And so I hope it makes some sense. I hope it's helped you guys a bit. If you're still confused, let me know in the comments down below if you really don't get it. Maybe I can remake this video in the future or something. But I think this is as clear as I can make it right now. And at this point, I do want to jump into the code because we're getting a bit long here on time. So let's dive into the code. Maybe that'll help clarify it some more. Whoops. There we go. So let me see here. I'm going to move this over just a bit, and we're going to start with kind of with our standard error checking like we did before. I do have a couple of notes here again that I pulled up on this code, and I'm looking at those this time around just because I want to keep it as close to possible as the other two videos so you can at least see some similarities. For the actual order checking, we're going to say if not pre-order, or not post order. If one of them is missing, we're going to return none. Again, I don't think that'll be an issue here. We should get all bona fide, legitimate inputs, but just in case. We're then going to create another builder function like we did before. And for this one, we've already kind of clarified what parameters we're going to have to put in. So we're going to have to put in these four, which are going to define where we're going to start and end in our pre-order when we're determining what part of the tree we're going to be creating. And we have to do that as well for the post order traversal. So I'm going to just go ahead and call these pre-start, pre-end, and then I'll say post-start and post-end as well. And for now, I'm just going to write pass here and just kind of leave it. We'll fill that in a second. And then like we did in the other videos, and I mentioned we would here, we're going to have to create some sort of mapping that'll help us find the values in the pre-order tree in instant time or in constant time in the post order, so we can determine where those boundaries are going to be. That's where I kind of referred to this post index and our ability to search up in constant time where we are in post order with respect to pre-order. So I'll just call that post index map, kind of like how I called it in index map in the previous videos. And we'll say for index and value in the enumeration of the post order table, we are just going to say post index map of the value. So we want to know what index the value is at. Okay, we want to know what index the value is at, and that's what these two lines of code will do. And finally, we're going to want to return. We're just going to make a call to builder. So all we're going to do is call this function once. We'll do all recursion in here in this, and this is where the meat of it's all going to be, where the meat of all of this is going to be. Sorry, I'm getting tired. And we're just going to return the tree as it is. So a couple things we're going to have to put in here. We said we wanted to pre-start and pre-end and post-start and post-end. Well, we're going to start those, and they're going to be pointing at the start and end of each array respectively. So we'll start the pre-order at index 0, and the final one at the length of pre-order -1. And post-start is going to start at 0, and at the length of post-order -1. I don't think I'm breaking any brains here with this statement. Now, we'll think about the terminal conditions in a second. So I'll put terminal conditions here just as a note. We'll dive into them. I want to make the bulk of that logic first, and then we'll fill these in. I know I'm going to have to create a root. Okay, so I'm going to have to create a root using some sort of values. I'm going to have to set root.left equal to something. I'm going to have to set root.right equal to something. And eventually at the end of this, I'm just going to want to return the root. And this is kind of like my anchor. I'm going to have to do a bit more work in here, and I'm going to have to define how we're going to make these calls. And in fact, we know we're going to be making them to builder, so I can do that. But like I said, we will define kind of what we're doing in here. Again, I wanted to anchor myself and kind of set my head straight on what I'm going to need to fill in. So let's imagine what's happening now. I'm making my first initial call here. And on my first call, I want to pull up this root right here, this one. And so what I do then is I'd call the tree node class, and I've erased the notes here, but when you kind of pull this question up from scratch, they give you the tree node class, and they tell you that, it's called tree node, and it takes the value. So the value that we're going to take is, again, the first index of the pre-order traversal. Now, sorry. Oh man. I'm going to take preorder, and I'm going to have to refer to a specific index. The index that I want is always going to be my pre-start index. In this case, it's 0 by default, and so this will allow us to kind of simulate almost that pre-order walkthrough that we used to have. But again, it's now it's going to slightly depend on what part of the tree we're calling. So that's that. Then what we had to do is we had to determine, you know, we understood how we're going to make these calls. And when we make our left subtree, we can maybe even feel like we know we're going to have 4 variables in here. And we said that what we're going to need to do in order to find what these variables are is we're going to need to find where this counterpart is, right over here. And we're going to need to find what the length of this subtree is going to be, right? So to find that kind of counterpart in the post order traversal, I'm going to call that index post index, and I'm just going to refer to post index map. And within that map, I'm going to look for not the node value that we just created, but the one after that. So we just created the 1. I'm interested in the 2. So I'm interested in looking for the value that's in preorder, not at pre-start because that's the 1. I'm looking for the one that's 1 after that. Okay, it's going to be 2. So the one right after the root that we created. With that, I'm then going to have to determine what the length is going to be of our subtree. So this is the length that I was talking about right here. The length is going to be equal to the post index that we just saw minus post start plus 1. And the reason we're doing that is, you know, we always kind of do this with indices. And reason being, imagine we had this index here is 2 and this index here is 0. The distance between these two inclusive is 3. So we're taking 2 minus 0 plus 1. That's how we're getting the length here. And finally, all that's actually left is to input where these boundaries are of the tree that we're going to be making. Now, this is where we had all this fun over here in defining these. And so we kind of acknowledged how we would go about putting those in. We said that we're going to start at not the root, but 1 item over for the beginning of our left subtree. And it's going to go for an additional length units. So it's going to start at preorder plus 1, pre-start. And I think, am I doing this correctly? Pre-start plus 1, and then it's going to end at pre-start plus length. Okay, pre-start plus length, exactly how I did it here, which will take us from the 2 to the 5. Now, the left subtree as well, we said we need to define what the post-order boundaries are going to be. The post-order boundaries are going to be from the beginning, so from post-start up until this post index that we just found, or you can call it post boundary, because the end of this tree here, well, 1 unit after that is going to be the beginning of the next one of its counterpart, of the right side counterpart. So that's why I called it post index, just maybe for lack of a better term. So the left side is going to start at post start, and it's going to end at post index. And let me make sure that's also, we had here post start and post index. So this is how we figured out what the parameters are going to be for when we're calling the creation of the left root, or the left subtree of the root. Now we've also got the right subtree of the root to worry about. And we said that here, that is going to be starting, you know, 1 unit over from this boundary here. And for us, this boundary was pre-start plus length. So this has got to be pre-start plus length plus 1. So it's going to be pre-start plus length plus 1. So this one, you know, this was the end of the left subtree. So the beginning of the right subtree is right here, right? The end of this one is just going to be pre-end. So we're just going to go all the way to the end here, and that's going to represent our right subtree. Now, again, finally, we're going to need to do this for the post order as well. Whoops. The post order is going to start at this, at this 6, which was equal to post index plus 1. So post index, again, this magical number we found right here where our boundary is, post index plus 1. And it will go, so originally we were tempted to say it'll go to post end, which is all the way over, but post end is the root we just created, right? So we're going to have to go to post end minus 1, right? Post end minus 1. I know the code seems a bit confusing here, but again, I hope the logic we walked through beforehand kind of justified why this looks how it does. The only thing I haven't done yet is the terminal conditions, and so I wanted to get a bit acclimated to the use of these variables, and I think now the terminal conditions make a bit more sense. Namely, if we get something funny, like where we get the pre-start is greater than the pre-end, then we're going to want to return none. So if for whatever reason we make a call, we've kind of crossed over that boundary and we're almost going the opposite way, it means we've gotten to like a null node. It's one that doesn't have any subtrees. It's not a node itself, and that's why we're just going to return none here. Otherwise, if we get in a scenario where they're equal to each other, so imagine that we call this function, or this pre-start and pre-end end up equaling each other, means we're just looking at one node. Well, that node must be a leaf node. Like we must only be looking at this one item. And so at that point, we actually just want to return a node of that item itself. And so that'll be a tree node that actually looks like this. So maybe I'll copy and paste this over. We're just going to return this bad boy as is. You could argue that this isn't really a terminal condition, that I could get rid of this, and I could do something like if pre-start equals pre-end, then return root. Yeah, you could argue that, and then kind of get rid of this. Whatever floats your boat. I liked it like this. It was cleaner for me in my head, so that's why I ran with it. So technically speaking, you could argue that this is our terminal condition. And again, the reason I'm actually using pre-start, pre-end here, not post-start and post-end, is because I'm doing my walkthrough this way, and I'm using the pre-index to create my root values. Nothing stopping you from doing it the other way around and kind of creating this one here and working backwards. In which case you could kind of use this. You could use the post, start, and end here, and then you could create using your post order at post start. And that should be it, guys. So I'm gonna push run here real quick. Pre-start is not defined on line 12 because I didn't capitalize it, and that means I made that mistake here, and I made that mistake here. And let's see where else I made it. Nowhere. It was too good to be true, and I almost had it done. There we go. So as you can see, I really moved this over here, but the result's good. This is a quick. I believe it's the optimal solution. So we will be doing this in. I'll move it a bit further over so you can see. There we go. We are doing this in linear time and space. I guess the space could be the size of the recursive stack, which would get the O of height, if you will. Though again, you can argue it would just strictly be O of n because we've got to create a node reference for every possible node in the tree. And in linear time, we're not really tapping any units twice. We're just going one item at a time, banging them out, making it super efficient. Yeah, this one was loaded. I know it was a medium problem. I would argue that this could be a hard. I at least found it really not intuitive. I like to do a summary usually at the end of my videos, but I feel like this will become a very long summary, and I've already tried to do it kind of as I went. So I do urge you, if you're kind of on the fence about this one, try to give it one more view. Leave comments and feedback, of course, down below if you have any questions, anything that's left unanswered here. Otherwise, I hope you guys enjoyed this. I hope you learned something, and as always, I'll see you in the next video. I almost messed that up. Peace.